Lawrence Krauss. He's the director of the Origins project at Arizona State University. He's a bestseller author. His most famous book is The Physics of Star Trek. He recently published a book on Richard Feynman's contribution to science, and he's got a new book coming up which will be called A Universe from Nothing, and basically you'll be given the whole book in 30 minutes today. So please welcome Lawrence Krauss.
Thank you.
Thank you.
Thank you. You won't be given the whole book. I would never give it away. You have to buy it. But I will talk about some of the subjects that are in that book. And I put up this quote and then one of my favorite quotes from an author about mystery. Religion and science were both developed, I think, for the same reasons. One, to try and explain a universe that was completely unfair and unsympathetic, and to try and understand the mysteries of existence. Now, one of them stopped doing that a few thousand years ago, and the other has taken over. And I want to spend a little time talking about just that. Now, I've really enjoyed, that's the title I'd rather give. One of the questions that is often asked, in fact, has been asked of me many times, when people try and argue that science alone is not sufficient to describe the universe, is this age-old question that goes back before Plato, but St. Augustine and others, and Aquinas promulgated it, which is, why is there something rather than nothing? Somehow that question is supposed to imply there must be a God. That if we cannot explain why there's something rather than nothing, then science is impotent. And what I want to do is spend a little time talking about why that question is passé, because in fact science has changed the way we think about the universe, in particular the way we think about something and nothing. Now, I've really enjoyed the morning, and I really enjoyed the demonstrations, the numerous demonstrations that outmoded religious thinking is both stupid and irrelevant. But I'm going to take a different tack, which is happy, because I spend too much of my time in the United States making those arguments, often with my friend Jeannie Scott. I want to not spend time talking about religion. I want to spend time talking about science, because in order to understand why those outmoded views are outmoded, you have to understand what we understand. Now, I know many of you have been kind enough to come up and tell me you've seen me on TV or videos, and so I don't want to repeat all of that, but nevertheless, I'm going to assume that not all of you are experts on cosmology anyway, and I'm going to spend the first hour or two talking a little bit about what we know about the universe, and then I want to talk about the concept of how it relates to this particular question, which I've thought a lot about in writing the new book in response to a lecture I gave in which there was a lot of interest. Okay, good. Oh, there we go. It comes back. Now, the first thing I want to do, so I want to spend my time celebrating knowledge rather than criticizing ignorance. And the knowledge I want to celebrate has come from the last 50 years at least, but we are in a golden era. That it is amazing. We are living at a very fortunate time when our picture of the universe has changed more in 2 decades than it may have in the rest of human history. And we're exploring nature on scales that I would have thought when I was a graduate student were impossible to explore. And it is really an amazing time to be doing science, and wonderful. And I want to convey some of that, because we should celebrate it, and more people should celebrate it, which is one of the reasons why I spend my time writing and lecturing as well as doing science. But I want to summarize what we've learned in this context of the question that I was supposed to answer, which is that the universe isn't designed for us. So what we've learned is, as I'll explain to you, we're much more insignificant than we thought before. And we are a bit of cosmic pollution. If you get rid of us and all the galaxies and all the stars and all the aliens and everything, the universe is largely the same. We are cosmically insignificant, a bit of pollution in a universe full of dark matter and dark energy. All evidence, as I'll describe, suggests the universe, in fact, did come from nothing. I'll tell you how. The laws of physics as we know them may, in fact, not be profound, but merely accidents. And that's not that depresses some people, but since we're merely accidents, I don't see that it's a big problem if the universe is too. And for those that take solace in somehow our existence, I want to remind you that the universe the future is miserable. The universe we live in is probably the worst of all possible universes to live in as far as the future of life is concerned. In fact, when I gave a lecture on this subject, for which the book eventually was caused because it became a YouTube sensation, the title was A Universe from Nothing, I think, but the subtitle was We're All Fucked. And in any case, but I'm not using that in the title of the book. Okay, so now let me give you a primer in modern cosmology to tell you how amazing the universe is. We are trying to understand what the universe is made of. It's the kind of question that people have been around since the dawn of civilization. And one way we want to do that is we want to weigh the universe. And it is amazing that we can weigh the universe. We do it by standing on the shoulders of giants, in fact. But this is a picture that allows us to weigh the universe in many ways. It's a picture of a cluster of galaxies. It's a Hubble Space Telescope picture. And like all Hubble Space Telescope pictures, it inspires the imagination. Every dot in this image is not a star, but a galaxy. There are 400 billion galaxies in the observable universe. Each one contains several 100 billion stars. This cluster of galaxies, all galaxies live in clusters almost. We live in a cluster called the Virgo cluster. They like to cluster together because of gravity. This particular cluster is about 5 billion light years away, which means the light was emanated from these stars 5 billion years ago before the picture was taken a few years ago. So the light from these stars was emanated before our sun was formed. It took 5 billion years to get to us. That means many of the stars in this picture no longer exist. Most of them have gone out. Most of the civilizations that may have existed around those stars may have died. So just looking at a picture like this should inspire the imagination in a way that no myth or fairy tale should. But we can do more with it, because this picture is an example of an amazing phenomenon, which is the fact that space curves in the presence of matter, as predicted by Albert Einstein, who did his PhD here many years ago. You don't have to be a rocket scientist to see that there's something strange in this image. There are all the galaxies are yellow, but there are these weird blue things. These weird blue things represent something that Albert Einstein first predicted, although he thought it would be irrelevant. And I want to just give you a little bit of history, because it's amusing for those of you who may be scientists here and struggle to publish. It used to be a kindler, gentler world. And in 1936, in the journal Science, one of the preeminent science journals in the world, this article was published. This is how it began. You try and write an article like this nowadays. Some time ago, R.W. Mandel paid me a visit and asked me to publish the results of a little calculation which I had made as his request. This note complies with his wish. It's just so pleasant. Now, the person who wrote the article had some credence already, so they published it. But what was an article that proposed something which Einstein discovered, theoretically, but he said it would be irrelevant. He thought it would never be useful, which is the fact that because mass curves space, mass can act like a lens. If I have a bright object behind a very massive distribution, the light can curve around it and come back and be focused and magnified as my glasses magnify nearby objects. Or if I had a cut glass goblet and I looked through it, I'd see many images of you. And mass should be able to do just that. In fact, this was the calculation that Einstein performed. He thought it was so unimportant, in fact, that he forgot that in 1912 he'd done exactly the same calculation and thrown it out. And he said it would be irrelevant. In fact, if you go back in the journals, you can find the response he made to the editor, which I particularly like. He said, "Let me thank you for your cooperation with the little publication which Mr. Mandel squeezed out of me. It is of little value, but it makes the poor guy happy." That's how science is done. He didn't think it would be useful, but in fact it was, because the picture I showed you was of gravitational lensing. All of those blue images were multiple images of a single galaxy located 5 billion light years behind that cluster. And all of the images were created by the fact that mass curves space. It's an amazing contribute to the realization of general relativity. But more importantly, we can use it to weigh the universe because we understand that general relativity works, and we can ask the question, how much mass is in that cluster, and where is it distributed in order to produce the image? It's a very complicated mathematical problem, but you can solve it. So we take this image and we invert it, and that's where the mass is. In order to create the image you saw, the mass has to be here. Now, all the spikes are where the galaxies are. But the first thing to realize is that most of the mass here, this giant mountain of mass, is where the galaxies aren't. It's where it's dark. There's 50 times as much mass in that picture as meets the eye. Physicists, with their incredible linguistic perspicacity, and I hope the translators can translate that word, have called this dark matter because it doesn't shine. Most of the mass of the universe we've discovered, probably 40 times as much mass as is contained in all the stars and galaxies that we can see, is made of some invisible stuff that doesn't shine. This is remarkable, and it's what got me as an elementary particle physicist interested in cosmology. Because clearly it's the dominant stuff in the universe, and if we could figure out what it was, in fact, we could, as I'll argue in a moment, I thought we could figure out how the universe would end, and I wanted to be the first person to know. It seemed like a good idea at the time. We now know, for very good reasons that I don't have time to explain, that this material is probably made of some new type of elementary particle. Not made of any of the stuff that we see in this room normally, but that means that it's not just out there in the galaxy and in all these galaxies, it's in this room going right through your bodies as you're dozing off here. And that means we can do experiments to detect it. Or we might actually create it. And one of the very exciting things for us right now is that we're building experiments underground to try and look for these particles as they come through the Earth. And again, I don't have time to explain how we're doing that. But another possibility is we might create them if we build a large accelerator, as we've done outside Geneva. The Large Hadron Collider may create these particles that were first created at the beginning of time. And it's fascinating because we may discover the nature of reality, what makes up the universe. But it doesn't matter what the stuff is. We can say from this picture how much of it there is. And one of the great discoveries of the last 20 years is to add up all the matter in the universe, and we come up with the answer. Here it is. I can tell the size of amazement. Well, in physics, when we come up with an important number, we give it a Greek letter to seem scholarly. And we call it omega. But what this is the total amount of mass in the universe in matter. And what it is the ratio. As I'll show in a moment, Einstein told us that space could be curved. And that means the universe can exist in one of three types of forms. So-called open, closed, or flat. A closed universe is one with enough matter that space closes in on itself. So if you look far enough in that direction, you'll see the back of your head. Okay? An open universe and a flat universe are infinite in spatial extent, and we want to know which universe we live in. And it turns out as you add more matter to an open universe, and eventually you close it. And a flat universe is the boundary between the two. And this is the ratio of the total amount of matter in galaxies and dark matter divided by the amount you'd need to make an exactly flat universe. So this was the holy grail of cosmology for much of the 20th century. How much matter is there, and is there enough to make the universe flat or closed? And we now have discovered, apparently quite convincingly, that there's only 30% of the amount of stuff in the universe needed to make it flat. The universe is open. This is a remarkable observational discovery. However, theoretical physicists like me knew it was wrong. Because theoretical physicists know the answer to every question. They're not often right, but we always know the answer. And in this case, we knew the universe had to be flat because a flat universe is the only mathematically beautiful universe. And in particular, as I'll describe momentarily, it's the only universe that could come from nothing. And here these damn observers were coming up with the wrong answer. Well, it turns out this is a ridiculous way or a difficult way to try and measure the curvature of the universe by using mass and then general relativity and determining the curvature. Why don't you measure the curvature directly? And one of the other amazing and unheralded discoveries of the last decade or so is that we can measure the curvature of the universe directly. And we've done it, and I want to show you how. And then I'll get to the implications. I think I'll forget that. So here are these pictures of an open, closed, or flat universe. I think I'll skip that. Well, I won't skip for one point. If you want to determine if the Earth is flat, you can go around it. But if you can't go around it, how could you do that? Well, simply, you could ask a European high school student, what are the total number of the sum of the angles in a triangle? You'd ask a European high school student because an American high school student couldn't give you that answer. And the sum is 180 degrees. But that's because they learned the geometry from Euclid. On a sphere, as you can see, these are two-dimensional universes. The real universe is three-dimensional, but I can't draw curved three-dimensional universes. A triangle, the sum of the angles are different. And in an open universe, again, different. And it turns out it's true even for three-dimensional curved universes. So if we could try and find a triangle that's big enough and measure the angles, we could measure the curvature of the universe, and we've been able to do it using the most important discovery in cosmology and much of science, the cosmic microwave background radiation, the afterglow of the Big Bang. Radiation that's been coming at us from the Big Bang. It was discovered by accident in New Jersey, of all places, in 1965 by two people who didn't know what they were doing, but they won the Nobel Prize anyway, because you don't have to know anything to win a Nobel Prize, you just have to discover something. And what it is radiation coming at us from the Big Bang. If we look out back in time, when we look out at distant galaxies, we're doing cosmic archaeology. We're looking back in earlier times, and galaxies that are 1 billion light years away, the light came 1 billion years ago from them. Well, if the universe is 13.72 billion years old, which it is, except in Arkansas and Ohio and a few other places in the United States, then you would think if you look back 13.72 billion years out, you would see the Big Bang, and you would in principle. But you can't, because between you and the Big Bang, there's a wall. Not a physical wall like this, but essentially one. I can't see past this wall because the wall is opaque. If I look back in time, the universe was hotter and hotter and hotter, and at a time when the universe was 100,000 years old, it was a temperature of 3,000 degrees Kelvin. At that temperature, the radiation is hot enough to break apart matter into charged particles, protons and electrons, and form what's called a plasma. And a plasma is opaque to radiation. You can't see through it. So if you look out, well, what happens is at early times the universe is opaque and you can't see through it. But then at the moment the universe becomes neutral, when protons can capture electrons, when the universe cools down below 3,000 degrees, it becomes transparent, and you see the radiation coming from that last moment, what's called the last scattering surface. And that's the radiation we've seen. It's cooled from 3,000 degrees to 3 degrees. That was discovered in 1965, the afterglow of the Big Bang. Now, if we look at that picture, and I'll show you a picture of that radiation in a moment, one scale is very important, 1 degree across. Why? Because 1 degree represents about 100,000 light years. Now, Einstein told us that no information can travel faster than the speed of light. That means if the universe is 100,000 years old, nothing that happened here could affect anything over here because light can only travel that far. Equally important, if I have a lump of matter, well, it starts to collapse due to gravity, and all sorts of things happen if the lump is that small. But if the lump is this big, it doesn't even know it's a lump because gravity can't travel across it. So it doesn't start to collapse. So the biggest objects that can collapse are this size. But that gives us a triangle. Oh, I'll draw it here. It means if we look here and measure how big are those lumps, how big are the lumps on that surface, we can determine the geometry of the universe. Because in a flat universe, light rays travel in straight lines. And that will subtend an angle on our eye of 1 degree. But in an open universe, light rays bend outwards, and the same ruler that's 100,000 light years across will look smaller. And in a closed universe where light rays converge as you go back in time, the same ruler will subtend a bigger angle on our eyes. It'll look bigger. So we just have to look at those lumps and ask, are they 0.5 degree, 1 degree, or 2 degrees across, and we will measure the geometry of the universe. And we've done it. We did it first with an experiment here called the Boomerang Experiment in Antarctica. We had a microwave receiver on a balloon that went around the world, which is very easy to do in Antarctica. It's very easy at the South Pole. You just do this. But they did a little further away. It took 2 weeks to come around. And this is the image it returned, a false color image of that radiation. These are the hot spots and cold spots in that microwave background radiation. These are the primordial lumps that would later collapse to form galaxies and stars and people and everything else. But the question is, how big are those lumps? Because that determines the geometry of the universe. And to test that, well, here's a different false color image of the same region. And we can make universes on a computer. And here's a closed universe, an open universe, and a flat universe. And you can see that in a closed universe, the average 100,000 light year across lump would look this big on our eyes. But this is bigger than these lumps. In an open universe, the average lump would be about that big. But that's smaller than these lumps. But just like Goldilocks, in a flat universe, it's just right. In fact, we now know to an accuracy of 1% that the universe is exactly flat. Just like we thought. But there's a problem, because I just explained to you, we showed the universe was open. Well, there was a problem with that picture. We weighed clusters of galaxies. We weighed the mass in the universe. We now know there's only 30% of the necessary mass in the universe, or energy in the universe, to make the universe flat. That means if the universe really is flat, we're missing 70% of it. Where could that 70% be? Well, if it isn't around galaxies, it's where galaxies aren't. What is where galaxies aren't? Nothing. Empty space. So all you have to do is give empty space energy and you solve the problem. If you take a region of space, get rid of all the radiation and all the matter, if it weighs something, then you solve the problem. But that's insane. Empty space can't weigh anything, you'd think. But cosmology is a science, not philosophy, so we can go out and test that. Because Einstein told us if you put energy in empty space, it's gravitationally repulsive, not attractive. And if you were trying to measure the expansion of the universe, as happened about 10 years ago, observers were trying to measure the rate at which the universe is expanding as a function of time, and everyone expected that the universe was slowing down because gravity is attractive, or as anyone who's taken physics knows, gravity sucks. It should slow down. In 1998, however, and I don't have time to explain how we can measure this, it's using objects called exploding stars, supernovae, which are fascinating, and illustrate a fact which I really do want to remind people of. It's important for understanding evolution and complexity, is that the universe is big and old, and rare events happen all the time. Because they happen, it doesn't mean they're significant. They're just accidents, but they happen all the time. And stars explode all the time, it turns out. And by measuring these stars at different regions, we could actually try and determine if the universe was slowing down and the rate at which it was slowing down. And to figure that out, we draw a straight line through this distance versus velocity curve, put the whole thing down horizontally, and if the universe were slowing down as everyone thought, all of these supernovae should follow that curve. But much to the shock of the observers, all of these objects lay above the straight line. And the only way we can understand that, unless the data is wrong, is if the universe is speeding up. If the expansion of the universe is accelerating. And the only way we can understand that is if we put energy in empty space. And if we ask, let's just fit this data and ask how much energy would you have to add in through empty space to fit the data, you get exactly what we were missing. If you put 70% of the energy of the universe in empty space, then you produce exactly what we see. So we now have a consistent universe of a picture of a cockamamie universe. Cockamamie is a scientific term. Crazy universe that is a sea of dark matter and dark energy. 70% of the energy of the universe resides in nothing. 30% resides in dark matter, and the error between the two, less than 1%, is everything we can see. That's why you are indeed much more insignificant than you may have thought before you heard the lecture first. But that implies many things about the future. and the present. And that's what I want to spend the last few minutes of this talk talking about. We have discovered this remarkable and totally inexplicable fact. In fact, we have no idea why empty space has energy. It's the biggest mystery in science. And if anyone tries to explain it to you and tell you they understand it, they don't. Especially if they're a string theorist. As I'll explain. But its existence, we think, is probably tied to the very beginning of the universe, and it will determine our future, which is why our future is miserable. It has changed everything about the way we think about the universe. But I want to now talk about this for a second, because I want to spend the rest of the talk talking about this nothing. What is nothing? Well, it turns out, once you put quantum mechanics together with relativity, nothing isn't nothing anymore. It turns out empty space is a bubbling, boiling brew of virtual particles that are popping in and out of existence in a time scale so short you can't measure them. They're called virtual particles. Now that sounds like philosophy or religion because it sounds like counting angels on the head of a pin. If you can't see them, then what's the point? Well, it turns out we can't see them directly, but we know they're there because they're responsible for many things. In fact, this is an animation which was shown in Stockholm 7 years ago by the winner of the Nobel Prize, who is one of a group of people that tried to understand the strong force between quarks that holds together quarks into protons and neutrons, which make up all the stuff in your body. Well, it turns out if you take a proton in your body and look at it, it's made of 3 quarks, but you add up the mass of those quarks, it's not the mass of the proton. Most of the mass of the proton is understood as being due to these virtual particles popping in and out of existence, and this is an animation, but it's taken directly from the mathematics. They're responsible for 90% of the mass of the protons in your body. Therefore, they're responsible for your existence. So even though we can't see them directly, we know they're there. So we know that virtual particles can give energy in the empty space inside of a proton. Maybe virtual particles can give energy to the empty space in the universe. The problem is when we try and calculate that using the same formulas that we use here, well, the answer comes out to be wrong by 120 orders of magnitude, which is the worst prediction in all of physics, so we usually don't talk about it. And that is one of the reasons we don't understand why empty space has energy. It's not that we don't understand why it has energy. Why does it have so little energy? Why does it have 120 orders of magnitude less energy than our theories predict? We don't know the answer. But it's certainly possible that empty space has energy. Empty space, or nothingness, is not empty. In fact, nothing is unstable. Nothing always creates something because of the laws of quantum mechanics. Now, the other thing we need to know about the universe is that gravity is kind of strange. In a flat universe, every galaxy has 0 total energy in a gravitational sense. That's because gravity allows positive energy and negative energy. And the two can add up to precisely 0, which they do, and they only do in a flat universe. It's very strange, but true, that gravity allows negative energy configurations. Again, I don't have time to explain that. But that allows for another fascinating possibility. You can start out with nothing and end up with something that has positive energy as long as you counter it with lots of negative gravitational energy. And that's exactly what we observe in our universe. We observe galaxies and stars and people that have positive energy. But when you add up their energy, their gravitational energy, and subtract from it the gravitational attractive energy between stars and galaxies, the two add up to precisely 0. But this allows for another more interesting possibility. Because as I'll point out, many religious people, when I and my colleague Stephen Hawking have argued about this with them, have said, well, you're not talking about nothing. The nothing you're talking about is not nothing. It's something. It's nothing plus quantum fluctuations and all sorts of other neat things. It's maybe empty space. It may have been the nothing that Plato or Aquinas talked about, but it's not the nothing we want to talk about now because it's got fields and quantum mechanics and all that stuff in it. It may be empty space, but it's not empty. But this allows another possibility, because when you apply quantum mechanics to gravity, then you find out not only can you create virtual particles that pop in and out of existence in a pre-existing space. But you can have space itself pop in and out of existence. You can create universes out of nothing. And in fact, quantum mechanics tells us that if the total energy of that universe is precisely zero, you can create it with impunity by quantum mechanics. So now you have a whole different kind of nothing. You have no space whatsoever, and it can be created by the laws of quantum mechanics, but only exist for a long time if its total energy is zero, which is precisely what we see today. Okay, so that's what I've said. Now, this alone is not sufficient. I was amused when I understood exactly when I listened to the talk about the Turin Shroud, is every time you disprove something, people who strongly believe it will come up with another reason why another redefinition of the same term, so that they can continue to believe what they knew to be true before you asked the question. And so we've gotten rid of two kinds of nothing: empty space, which can create particles, and now no space, which can create space. But that isn't good enough for many people, as I'll talk about. The question is it really nothing if you create space? Well, people have said, well, that's not nothing, because you still have the laws of physics. Who created the laws of physics? There, you need a deity for that. I want to try and demolish that last viewpoint in the last 5 or so minutes of the talk. And it comes from this remarkable fact that the universe is dominated by the energy of empty space, but it's a little weird. This is the most complicated figure I'll show, so it's downhill from here. This is a brief history of time. This shows the density of matter in the universe as the universe expands. The density of matter goes down as 1 over the volume. As the universe gets bigger, the density goes down. This is the energy density of empty space, which remains constant. Because there's nothing there, it doesn't get diluted. We are living, if our current picture is correct, right here. But this is a very strange time, because it's the only time in the history of the universe when these two quantities are almost the same. Now, Copernicus told us we don't live in a special place or a special time. So why should we live in the only period in the history of the universe when those two numbers are the same? At much earlier times, the energy of matter was much bigger than the energy of empty space. At much later times, the energy of empty space will be much bigger than the energy of matter. Why? This has caused physicists problems. And the answer one group has come up with is that galaxies exist. Now, why is that? Well, if the energy of empty space were, say, 50 times bigger, these two curves would still cross, but at a different time. But if it was 50 times bigger, they'd cross at the time that galaxies first formed. But the energy of empty space is gravitationally repulsive. If it dominated the universe before galaxies formed, galaxies wouldn't form. The repulsion would beat out the attraction. So this has led to an idea, which I call anthropic mania, that maybe there are many, many different universes. And in each one, the energy of empty space can vary. And then only those in which it's not much greater than we measure today will galaxies form. And only then will stars and planets form. And only then will astronomers form. So the universe is the way it is because astronomers are here to measure. Now you laugh. It almost sounds religious. It's not. If anything, in fact, it's just a very extreme version of natural selection. Bees can see the colors of flowers that they want to get stuff from so they can make what they need to live, because if they couldn't, they wouldn't survive. Similarly, if there are many universes, we would be surprised to find ourselves living in a universe in which we couldn't live. So really, it's not religious at all. It's just an extreme form of cosmic natural selection. But if it's true, it's very depressing. Because it means this fundamental quantity that many physicists like me would try and understand, the energy of empty space, is not fundamental at all. It's just an accident. Just like the Earth-Sun distance is not fundamental. It's an accident. If it were any bigger, we wouldn't be here. If any smaller, we wouldn't be here. But it's nothing fundamental. Now, this has led particle physicists who are much ahead of cosmologists to a different idea, because cosmologists haven't understood one fundamental number, the energy of empty space. But particle physicists haven't understood many more numbers for much longer. We don't know why gravity is the weakest force in nature, why the proton is 2,000 times heavier than the electron, why there are 3 generations of elementary particles. We don't understand lots of things. And particle physicists have jumped on this idea and said, maybe we don't have to understand anything. Because maybe everything is an accident. There are many universes, and in each universe, all the laws of physics are different. And only in the universe in which the laws of physics are what we measure will we be around today. Therefore, what we need is not a theory of everything, but a theory of anything. And we have such a theory. It's called string theory. So I want to spend one slide showing you what string theory is if you haven't heard of it. One person says to another, I just had an awesome idea. Suppose that all matter and energy is made of tiny vibrating strings. And the second person says, okay, what would that imply? And the first person says, I don't know. That's the history of string theory for the last 40 years. But what string theory tells us, if it argues, is that there are many more dimensions in the universe, 10 at least, and 6 of them get curled up, and only 4 are big enough for us to see, which is strange. But what's really unfortunate is that and the string theorists got very depressed about this, is that every different way you curl up those extra 6 dimensions produces a 4-dimensional universe with different laws of physics. In fact, it now predicts at least 10 to the 500 different possible universes with different laws of physics. And that used to be a bad thing, but now it's a good thing. Every wart in string theory becomes a beauty mark, because in every possible universe that involves a different way of compactifying those extra dimensions, you might have a different energy of empty space. And therefore, you're guaranteed to find one that has the energy we measure. Now, this is unfortunate if it's true, because it's not clear that it's really science. Because if your theory allows any possible universe, then how do you disprove that theory? But it still may be true. The universe is the way it is, whether we like it or not. And this may be true, as much as I hate the idea. But it does allow for a new possibility. It allows for the possibility that even the laws of physics themselves are not written down. They arise spontaneously when the universe arises. And out of this multiverse of universes, a universe can form truly from nothing. A universe in which the laws of physics are not even prescribed, nor is the existence of space, nor is the existence of matter. It all comes from absolutely nothing. And that, to me, is the ultimate version of nothing, and the one aspect of this picture that I like a lot. Because in some sense, it allows us to answer that question. Because one of the things that people say is if our universe began, what happened before our universe? But if there's a multiverse, it could have been eternal. And our universe would have popped out of it at some point. Other universes are just being born now. Other universes are dying. If even the laws of physics are accidental, then the last bastion against nothingness, it seems to me, falls. And that's very important. And in fact, I want to sort of end with a few sentences about nothing. The key thing I want to stress is that nothing and something are not philosophical concepts. They're not theological concepts. They're scientific concepts. Philosophers can argue till they're blue in the face, and they have, for 2,000 years about what is nothing. But it doesn't matter. That's just talk. If we want to find out what nothing is, we have to measure it. And what we find out is that the distinction between nothing and something is blurred. So that the whole question is, why is there something rather than nothing, becomes irrelevant. They're not that different anymore. In fact, people have now said to me, well, so none of this is nothing, because nothingness is really something which doesn't even have the possibility of existence. And in your multiverse, there's the possibility of existence. So true nothingness has no possibility of existence. But you would ask then the question, if that's the case, then how did God bring it into existence? If there's no possibility of existence. The possibility of existence is not equal to existence. The virtual particles that pop in and out of empty space did not exist before they popped out. The fact that they were possible did not mean they existed. If the possibility of existence were the same as existence, then there'd be as much of a controversy in my country about masturbation as there is about abortion. Think about it. So what some theologians have argued, or what people argue essentially to me, is that nothing is that from which only God can create something. But that's not much of a description about nothing. What we've now learned is that science has changed the playing field. And I think, I think I'll skip any discussion of God. It's irrelevant. I want to spend the last 2 minutes just reminding you why the future is going to be miserable so you can feel better about your day. The first person to realize, think about the future, was George Orwell, who said to see what is in front of one's nose requires a constant struggle. This is clearly what he meant by it. What this mathematics tells us is that if there's an energy of empty space, the universe is going to accelerate. That means objects will move away from us faster and faster and faster, and there exists a certain distance beyond which objects are already moving away from us faster than the speed of light. And that distance will decrease with time, because objects are going to be moving away faster and faster and faster. So the rest of the universe, and we can calculate when that's going to happen in about 18 billion light years, that's the distance, 18 billion light years. So objects will begin to disappear significantly when the universe is 18 billion years old. It's 14 billion years old now. This is beginning to happen. What it means is that as we look out at the universe, the longer we look, the less we will see. I've tried to use that in the United States as an argument to fund cosmology right now, but it hasn't worked. 2 trillion years is a little longer than this standard congressperson's firm. But what will the future bring? I would argue the future will bring back the ignorance that we once had. 100 years ago, we thought, and Einstein thought, we lived in a universe with a single galaxy located in a vast, infinite, empty space that was static. That was the picture of the universe in 1915 when Einstein developed general relativity. In the far, far future, around some planet, around some distant star, life forms will arise. They will learn the laws of physics, they'll learn quantum mechanics, they'll discover general relativity and electromagnetism, and they will use the best instruments they have to build telescopes, and they'll look out and they'll see nothing. In 1925, we knew of one galaxy, our Milky Way. In less than a human lifetime, we've learned about the other 400 billion galaxies. But in the far future, they'll have all disappeared. And observers in the far future will do the best science they can come up with, and come up with completely the wrong answer. They'll believe they lived in a static, eternal universe with a single galaxy surrounded by empty space. So the good news is we live in a very special time today. The only time when we can observationally verify that we live in a very special time. And I'm completely facetious when I say that. What I mean is as scientists, we're stuck with the circumstances of our own existence. Maybe there are things we could have observed in the universe had we evolved 5 billion years ago. Maybe there'll be things about the universe that we could see 100 billion years from now that we can't see now. But what we do know is if the universe continues to behave as if it is behaving now, all of the information about what is out there will slowly disappear. And that means in the far future, 2 things will happen. The illusion that we, and by we I mean whatever species is asking the question, the illusion that we are special will get stronger and stronger and stronger. Because in the far future, there will be just our galaxy. And it will look more and more as if the universe were created for us. So in the far, far future, we will be lonely and ignorant, but dominant. And those of us who live in the United States are quite used to that. Thank you very much. Thank you. Thank you. We have time for some questions? Do we have time for questions?
We are behind, but let's take 3, and please ask brief questions. Leave the comments to the lunch break.
Oh, it's all right. I'm good at cutting people off.
Yeah. Hello.
Yes.
My first question is,
my
only question. My only question is, if things right now, if we are in a special moment right now, and in the future, the one which will actually ask the question, will not be able to see there is more than this galaxy. Would you think that there will be a chicken and egg problem and say the ignorance of that people will be guided by the fact that they won't have access to any kind of knowledge, so that would actually lead them not being curious about the universe.
Well, look, I joined the last speaker in saying I don't make predictions, except about the universe. I like to think that intelligence is associated with both questioning and skepticism. And there'll be many interesting things to measure in such a universe. You'll have stars, you'll have planets, you'll have lots of interesting questions about life. How did life evolve? Learning the laws of physics, building quantum computers. There'll be lots to do, even though their understanding of the universe might be wrong on the larger scales. Just as today, and this is part of the conceit of particle physicists like myself often, is we assume, string theorists used to call their theory the theory of everything. The actual fact is, even if it was right, it's a theory of almost nothing. Because most of the universe is irrelevant. These questions of extra dimensions are irrelevant to understanding how oatmeal boils, or how climate changes. And so there's many interesting questions that can be asked even if we don't understand the universe on the larger scales, and we're proof of it. We've discovered most of the great physics of the 20th century without knowing that that most of these galaxies existed, or that the universe was accelerating. These are all recent discoveries. But one thing we're sure to know, and it'll be true in the future just as it's true today, is every time we open a new window on the universe, we are surprised. The universe surprises us in ways that our human imagination could never anticipate, which is why science is an empirical discipline. It's governed not by theories, but by experiment. And if we stop asking experimental questions, then surely we will stop having a civilization. Yeah.
Thank you very much, Professor Krauss, for this great talk. My question is about energy. You told us that empty space has energy. And is it now possible in theoretical physics that we get rid of the dark matter just by adding the energy to the energy of the dark matter to the energy of the empty space?
No, it turns out it's not, because energy comes in different types, and the gravitational behavior is very different. So dark matter, even though it's not made of the same stuff as us, falls in a gravitational field, and it clusters, and it forms galaxies and stars, and in fact, the dark matter is responsible for your existence. If the dark matter weren't here, our galaxy would never have formed, and the stars would never have formed. Whereas empty space has very different gravitational properties. And it is true that one type of energy can be converted to the other type, but when that happens, the behavior of the universe changes dramatically. For instance, one possibility is that the energy we measure in empty space now is just a transient. It's like when you cool down, we're in Zurich, beer, okay? You cool it down. Some of you have done this. You put it in the freezer because you want to have a quick drink, and you forget about it, and you take it out. It's liquid. You open the bottle. Suddenly it freezes, and the bottle breaks. That's because when there's a phase transition between liquid and solid, energy can be stored and suddenly released. It may be that the energy we're measuring in empty space is not the absolute minimum energy, that one day there'll be a phase transition, and that energy will be released, which would be fascinating. But it won't be fascinating for us. Because the minute that happens, everything that now exists will go away. So the good news is we won't know about it in advance. But the bad news is we won't get the answer to our question until we're not here anymore. Is there any last question or no? Maybe we should, people are hungry. One more. Okay, one more. I guess this young man here.
Thank you, Professor. Very brilliant talk. I just had one simple question about the even further future.
Okay.
Will the universe essentially go on forever, or will there be a time when I say the matter will just simply all vanish and there won't be nothing anymore except empty space?
Well, of course, again, we don't know for certain because we don't know all the laws of physics. We don't know what the energy of empty space is and whether it'll change. Nevertheless, as a theorist, I spend a lot of my time thinking about that, and I've actually written, as you may know, papers on this very subject. The picture that we now have, it's kind of like the Charles Dickens Christmas story, though. It's the future as it might be. I can't guarantee you it's the future, is dismal. Not only it turns out will the universe become cold and dark and empty because all the galaxies will disappear and all the stars will burn out and it'll get colder and colder and darker, but you can show, using simple laws of physics, that life must end. That life cannot persist forever, even in an eternally expanding universe. So the future, as we now think it will be a future of a cold, dark, empty universe, which you might call nothing. And as my friend Christopher Hitchens, who's writing the foreword for my new book, has said, based on my teaching him cosmology, if you ask the question, why is there something rather than nothing, in some sense the answer is just wait. Thank you very much.